talk. And this first talk will be around 30 minutes, and it's Agnes Kospal.
Thank you, Ellen. Thank you for the organizers as well. It's a great pleasure to be here. Yeah, so my topic, I was asked to talk about circumstellar environment of young eruptive stars. So I'm very glad that this conference focuses on this type of objects, so I don't have to give the introduction. So I would immediately start with my motivation. And for that, I simply copied open questions from our Protostars and Planet 7 chapter. So what are the current questions which we will need to answer? Of course, we would like to understand the role of variable accretion in building the stellar mass and determining the observed properties of protostars. It's a big question whether all stars experience large amplitude accretion outbursts as they form, or maybe these require special circumstances. It's a question what triggers the eruption events and what switches them off or temporarily stops them, like in this example where you see this temporary halt in the accretion. How can we use variability to evaluate instabilities that lead to bursts? And how well are we measuring accretion luminosity when we only have observation at a few or simply just one wavelength? And how does variability influence chemical and mineralogical processes that happen in the disk, which, of course, as the disks are the birthplaces of planets, will affect the formation of planets? So these are the motivating questions, and I will try to convince you that to be able to understand these questions, we have to, of course, study the environment of young eruptive stars. I was very happy to see when I was looking through the talks that we heard and we will hear throughout this week, and also the posters, that many of these questions are being addressed. So I will try to highlight some of these talks and some of the posters, but of course there are lots of works. There are also lots of papers addressing these topics in recent years' literature, and I have less time to read nowadays than I would like, so apologies if I don't cite your work. I will also focus on low mass objects. That's where I'm working as well, so apologies to the high mass object community and the very low mass object community. I will not really talk about chemistry as well, apologies to astrochemists. But as an introduction, after all, I will give a little bit of introduction. I will try to summarize what we generally understand about the environment where young stellar objects form. So I will start from the large scale environment and then go to smaller and smaller scales. So on parsec scale, I think that was one of the great results of the Herschel Space Observatory, that molecular clouds have filamentary structures. And these filaments, basically star formation is most intense in these filaments. These filaments also have substructures, and they are also fed by these striations, and they also have intersections where there is even more stars forming. And then if you zoom into what happens in a close vicinity of a star, of course, you form the disk, you start outflows, but you could still build up or feed this protostar system by streamers that may connect the larger scale environment streamers to the small scale environment. Now, if we zoom into, like, let's say, sub-parsec scales, so a few 10,000 or a few thousand AU scales, you will have the cloud core at the center. You can have a large scale molecular outflow jet, and then you first see the the more tenuous part of the cloud core, and then as you go closer, you will have you will see the denser envelope that is infalling. You will have a pseudodisk which displays this combination of infall and rotation, and then as you zoom in further, you will see the launch region, or at least the foot point of the outflow. Magnetic field lines are important, becoming important there, and then even closer to that, you see the Keplerian disk, and then the beginning of the disk wind. And then if we go to AU scale, by which I mean, let's say, from 1 AU to 100 AU, that's the scale of the disk. There are, again, all kinds of interesting structures in the disk. There are snow lines of different molecules. There is vertical setting and radial drift for the planetesimals and dust grains. In the disk, you have pressure maxima where these grains can accumulate and form gaps and rings. And then there are all kinds of observational techniques that you can use to trace these structures, different line observations to trace a gas or dust continuum for the thermal emission, or you can check the dust surface with scattered light observations. And then if you go even closer, then you will see this usual picture of magnetospheric accretion. Basically, as you go towards a star, temperature increases, so your dust disk stops at some point, and within that radius, you will have a pure gas disk, and then at some point, the magnetosphere of your star will divert the material, and the material follows the accretion, these accretion channels onto the star, where they hit the surface, accretion shocks form. Stars can have cold spots as well. And then whether an eruptive star accretes this way or not it's a question, because of course if the accretion rate is low enough, then a magnetosphere works as it should work. But if you increase the accretion rate to a very high level, then you may overwhelm the magnetosphere, and then you can have this kind of disks which touch the stellar surface, and you have the boundary layer. So in terms of how this is relevant, or what we can say about these structures, these scales for young eruptive stars, I will follow these three steps, starting from the largest scales. Start with the streamers. So if you look at the environment of young star, not only a young stellar object, but specifically a young eruptive star on parsec scale or sub-parsec scale, let's say, you may see signposts of earlier flyby events in the form of streamers, because flybys may perturb the disk and trigger outbursts. And that's maybe the case for Z Canis majoris, according to that paper at least. I know that this result is now contested, because that what we believe to be a streamer may actually just be a part of a larger outflow system. But then in other cases, like in FURI, there's a new result now that says that there is a streamer which is infalling, and these kind of infalling streamers may trigger gravitational instabilities in the disk if they are massive enough. Whether they are massive enough, that's a question. So there will be some talks later about the role of streamers and flybys. So we will learn more about this topic. Let's move to the jets and outflows. I think this is a very interesting topic. Whether CO outflows or jets, HH objects are present for FURs was already listed in this original table by Lee Hartman and Scott Kenyon from 1996. And you can see that sometimes they have none of these, sometimes they have one or two. And one example where we can see both a CO outflow and a jet present is a FUR like a peculiar object, V346 Normae. You can see an H alpha image, but you can see that HH object in all kinds of other tracers like a sulfur or other forbidden lines. And this also has a large CO outflow, which you can see in CO, obviously. So jets and outflows are interesting because the usual rule of thumb is that you have an outflow rate which is about 10% of your accretion rate. So of course, if there is an accretion outburst, there should be a corresponding increase in the ejection rate as well. And that also means that if you see that an object has a variable ejection, that could be an indirect sign of variable accretion. So for example, if you have a clumpy jet, for example, then the individual jet clumps may correspond to different accretion ejection events. Now, this connection is unfortunately quite tentative at the moment because of the uncertainties related to proving this direct connection. But again, there will be a talk later about this, and I also saw some nice posters that address this question. Now, again, if you consider fjords, for example, which have this accretion rate orders of magnitude higher than what is usual in normally accreting young stellar objects, you would expect that their outflows are also somehow large and massive and powerful. Whether that's true, that's a question, and that we try to address with my colleague Fernando here. We made a survey, a single-dish millimeter survey of 20 fjord-type objects, and a bit more than half of them display CO outflows, and these are indeed more massive than outflows of quiescent sources. We also found that the outflow envelope mass ratio is higher for fjords. The outflow forces were quite similar between fjords and quiescent sources. So one thing you have to keep in mind is that typically the dynamical ages of these outflows that you observe are much, much larger than the duration of the current outburst. So you have to consider their history. And what we think is that the accretion history might be similar, but fjord outflows may have lower velocities. It is also very useful to look at the outflows not with a single dish telescope, but with interferometry, because then you will be able to discern the different components of the, let's say, a few thousand, few hundred AU environment. And then you will, if you have the typical resolution you would need for this, considering their distances, is sub-arc second resolution and quite good velocity resolution. But with that, you can discern things like the molecular outflow, the expanding part of the envelope, the infalling part of the envelope, and the pseudodisk and the Keplerian disk, all kinds of components. And then this is an example of two different fjords, which incidentally show very similar structures with these wide, slow outflows. And it is also very interesting to look at these objects with high resolution, because they may surprise you with some interesting facts. And one interesting thing we discovered is that if you look at some of these fjord-like objects, these are both fjord-like objects following that classification, is that so on the very left hand side I show intensity maps, and then the velocity maps next to it with different CO isotope logs, different zooms. You see at the top that this object, HARO 5 ARS, has this narrow opening angle outflow. But if you zoom in, you will see actually two disks. The larger disk, the more massive disk, is the fjord-like object, but it has a companion, and we believe that it is actually the companion that drives this outflow and not the fjord. In the other case, this L1550 IRS5, this was also mentioned in one of the previous talks. This is a well-known, well-studied object, and it is actually a binary. So you see this beautiful, large, wide opening angle outflow, but if you look at the same system with the VLA, so the centimeter, then you can see that actually both stars drive jets. And then, so you have to keep in mind that when you zoom in, there may be not one, but two objects at the center. And then about fjord events in young binaries, there will be a talk. The envelopes are also, or the outflows are also interesting because there's a wide variety. Maybe the HARO 5 IRS5 is not a good example because it's not the fjord that drives the outflow, but there is a variety of opening angles from the very narrow to the very wide. And this gave us this idea with Hiro Takami that maybe these fjord outbursts operate in a way that when the accretion rate increases, also the outflow rate increases, and then you start opening up the angle of these outflows. And then after a while, of course, eruptions end, and then outflow also weakens, and then you can have replenishment from the outside if there's still some remnant envelope, and then the whole cycle can start. until you have enough material in the envelope, but then eventually you will deplete your envelope. So maybe the repetitive outbursting cycles are what drives a young stellar object on its way to become a disk-only class 2 source. And two contributions relevant here is late infall, which may rejuvenate disks. And also you can use basically measurements of these envelopes, for example, their molecular content, to look for past Fior outbursts. It's a poster of my PhD student, Liz Tricky. So far, I'm mostly focused on millimeter observations about the large-scale environment, but if you look at these objects in scattered light, you will see beautiful structures in scattered light as well. This figure combines data from Subaru and Sphere, and the interesting thing is that all the objects are scaled to the same physical scale. So some of these objects have this huge, very complicated spiral structure or outflow walls or arms and arcs, which we are not sure what they are or how they formed, but basically this is dust environment, and dust scatters light, and you can see that each of these objects is much more complex than our typical models. Now let's move on and zoom on to the center a bit more. And if we zoom in, the first thing we may see is a pseudodisk, and this we could measure quite nicely in case of a 346 Normie. You can see on the left-hand side this flattened structure, which we were wondering about what it is, because that's the millimeter continuum with ALMA. But if we integrate all the CO emission from the field of view, then you will see this very typical line profile of infall. But if you only integrate the central beam, then you will see a double peak line profile, which indicates rotation. So we measured basically the rotation, radial rotational curve, rotational velocity as a distance, as a function of distance along the major axis. And what we saw is that the inner part up to about 300-400 AU follows Keplerian rotation, but outside of that, it's subkeplerian. It's a pseudodisk. It's a combination of infall and rotation. And why that was, this is a sketch of the system, different components. And why that is really neat is because there's an analytical formula that you can use to calculate the infall rate, so how much material the pseudodisk transfers to the disk, to the outside of the disk. And that turns out to be 6 times 10 to minus 6 solar masses per year in this object, which is much higher than the quiescent accretion rate in this system. And by accretion, I mean what the disk transfers to the star. So in this case, at least, there's an evidence for a mismatch between how much material the disk gets from the outside and how much material the disk can dump onto the star, at least in quiescence. And that's very neat, because that means that material will accumulate, it will become unstable, and then you can have an outburst. Of course, to keep up these outbursts, disks have to be really massive, right? Well, that's, again, something to be checked, and that's something we really did check with Bauma Liu, again, another participant in this conference. So we did an SMA survey of 29 young eruptive stars, and we scaled their luminosities to the same distance, and what we found is that eruptive targets indeed had higher luminosities than normal class 2 young objects. There are some details if you look into the individual properties of these objects, but that was a promising hint. Now, most of the disks we did not resolve with SMA, but you can resolve them, or at least try to resolve them with ALMA, and that's what we did in this work. So with ALMA, we managed to resolve these disks so we could measure their characteristic radii. And also we made radiative transfer modeling. So we did not assume that the millimeter emission is optically thin, and that was good, because the masses we got from the radiative transfer modeling were 3 to 30 times more than the optically thin masses. So we believe that these are more accurate estimates for the disk mass. And what you can see here, data from this work and from the literature, is that FUOR disks are indeed more massive, but they're also smaller than typical class 1 or class 2 disks. And that gives a very interesting consequence, because that means that we can check whether they are gravitationally unstable. If they are massive and small, they may be unstable. There are multiple ways to check this, and one simple criterion we could check is that if the disk is more massive than 10% of the stellar mass, then the disk may become gravitationally unstable. And that criterion is fulfilled by, I think, more than 2/3 or maybe even 3/4 of this sample. So the majority may be indeed gravitationally unstable. Do we see signs for gravitational fragmentation, like in this numerical simulation? Well, at first we didn't, and we thought that, that's okay, these are faint objects, they're far away. Yeah, no surprise that we don't see it, but then there are persistent people who reanalyzed some of this data, and with the help of Philip Weber, we managed to actually discover some of these gravitational fragments really low level. You have to be very careful with the data processing in at least one of these objects, 961. There will be a talk about that later, so I won't talk more about that. Now, to equate millimeter fluxes with the dust mass is dangerous. We have to be careful because there may be non-black body components of the emission, and that was very evident when we observed the X-loop. We had different ALMA bands, and also with the VLA. So we have millimeter and centimeter emission, and the centimeter emission at least suggested a non-thermal component, or maybe free emission, but likely a stellar synchrotron, gyrosynchrotron emission, which doesn't have a black body spectrum. It doesn't come from the dust grains. So if you use that to estimate dust masses, that will mislead you. And a similar result for FUORI, the prototype of the other class. Again, lots of different emission components. So this contains free emission from ionized gas, and thermal emission from different types of optically thin or thick dust components with different temperatures, maximal grain sizes. And what is also interesting here is the binary and non-binary system. One is in outburst, the other one is quiescent. And you can see how different their disk structures are. Now, these are about the bulk of the disk or the outer disks, but if we are interested in what's happening at the center, we have to zoom in more. And how do you zoom in? Well, you take an interferometer, but not ALMA. You take an infrared interferometer, and that's what we did. We analyzed MIDI spectra. MIDI was the first generation infrared interferometer on the VLTI, and it observed a sample of 11 FUOR and exotype young eruptive stars, and we compared this with the sample of, again, normal quiescent stars. And what you see on the y-axis are basically half-light ready, so how large they are, as a function of the 8 to 13 micron color. And the eruptive stars are plotted with yellow, and basically we saw no significant difference in the structure of the inner disk. Inner disk here means a few AU. And now, of course, we have a second generation interferometer operating not only in 10 micron, but also in the M band, Matisse, which observed multiple young star objects already. This is the Matisse view of F Orionis. You can see the L, M, and N band spectra. And basically, without going into the detail about interferometry, we modeled these observations with the disk that had a central accretion disk component and an outer passive disk component. And what we found is that the transition between the two is at about 0.3 AU. So that's the size of the accretion disk, which I think is surprisingly large. At least some of the models predict that the disk region participating in the FUOR eruptions should be a bit smaller. And then another view, the Chara-Mercax view of F Orionis. We've seen this just a couple of minutes ago by Aaron Labdon. This, I think, is fascinating. So it told about it more, but basically their temperature gradient model predicts that there is an active accretion disk that extends down to the stellar surface. So at least about this object, we can be sure that the classical magnetospheric accretion model does not apply. Now that we heard his talk, we also know that there is another object, this V696 Pupis, which is very similar to FURI in this respect. Another object observed with MATIS is V900 MON. I won't talk too much about it. There will be a talk later by my colleague Claire Liku. But just shortly here, we see 10-micron features, which are different if you measure them at different baseline lengths, which corresponds to different spatial scales. And what we see basically is that there is a dusty disk which contains large grains, but there's a part in the center, towards the center, which is absorbed by small grains. As you go to longer baselines or smaller spatial scales, you will see that the 10-micron feature is more dominated by absorption. The fact that we see small dust grains towards the center of a FUR system is not surprising, because these may have dusty winds. The fact that these have strong winds are known for a long time. Here I'm just showing two examples from recent works of my colleague Zsófia Szabó, who reanalyzed some archival and new observations of two of the classical FURs, and some of these lines, for some of these lines you see these really deep absorption features, which are wind features, and they are variable. Strong variable wind signatures, and at least in the first case for V1057 Cygni, we saw that the profile of these absorption features correlates with the photometric variability of the object, which so the light curves show quasi-periodic fluctuations. So from this, we drew the conclusion that there may be some kind of a dust blob, which was lifted by this wind, dusty wind, from the surface of the disk, and that, of course, orbits with the Keplerian velocity corresponding to that radial distance, or some kind of disk inhomogeneity, dusty inhomogeneity. So yeah, there will be more talks about dusty winds and winds in FURs in general. So that's something which is not coming from interferometric observations, but with high-resolution spectroscopy, you can trace, again, very small spatial scales towards the center of these objects. About the accretion columns, I think a very good and very well-studied example is EX Lupi. This series of figures, I think, show a nice progression of our understanding of the accretion process in EX Lupi. So a very early result from 2012, led by Aurora Cecilia Aguilar, is that there is a very stable accretion column in EX Lupi, which has a variable throughput. That column is always there, it orbits, it connects the disk to the star, and what happens is that in quiescence, less material flows through it, and in outburst, there is more material flowing through this accretion column. So at least this object, we think, is doing proper magnetospheric accretion even in outburst. And then this new sketch shows a bit more understanding about non-axis symmetric disk structures and complex regions in the accretion flow. And then finally, these bottom series of figures are proper magnetohydrodynamic simulations of specifically EX Lupi system. Again, we will hear more about that. For that one, of course, what we need to know is the magnetosphere of the star, and now that is also measured. We have spectroparametric data from CFHT. I think there will be an online poster by Kim Pullin, my colleague, about these results. So we used Espono and Spirou spectroparameters on the Canada-France Hawaii telescope. We have multi-epoch observations, one set of data from 2016 and another from 2019. And on the left-hand side, you see these. You can see you can use spectroparametric observations to measure, basically using the Zeeman effect, to deduce the magnetic field. And of course, we don't resolve the stellar disk, but what happens is that during a snapshot observation, you measure the average magnetic field of the visible hemisphere, but then you do it a day later, you do it again a day later, and as the star rotates, you can basically map its full surface, well, at least that part which is visible, considering its rotational tilt. And on the left-hand side, you see the radial, azimuthal, and meridional component of the magnetic field, and on the right-hand side, the brightness distribution. What is remarkable here is that it shows a very slow evolution. So indeed, the magnetic field is also very stable. Bright and dark features on the stellar surface are very stable. It's a dipole-dominated field. It's strong both if you look at the small scale or the large scale magnetic field. And that is really interesting because this you can use to calculate the magnetospheric truncation radius, which then you can compare to a rotational radius, and you can constrain some models about this. So at least so we know EXOP accretes in a magnetospheric way. We know FURI accretes in through a disk that extends down to the stellar surface. So this may be related to their different accretion rates. Of course, in one object, there may be a transition between these two states, as we heard just a couple of moments ago. And now time is almost up, so I would like to just mention that, of course, I talked about variability, but the picture I drew about the environment may seem static, but it's not. There are hints already, or even firm results in the literature about millimeter variability. You can see variations in the continuum emission from the envelopes from the bulk of the disk, which indicates temperature changes. These things act as bolometers. You heat them up, they emit more. But also for line variability, which trace not only temperature variations, but also there may be chemical changes, chemical reactions that would not happen otherwise. You can also look at infrared variability, and that will trace changes in the inner FUAU region of the disk. There are fascinating ideas of moving snow lines with the changing accretion rate. So there are experiments that target this kind of phenomena. And if you can get your hands on monitoring observations with interferometers, then you can really trace real-time structural changes during and after an outburst. So I think these are now all possible with the current instrumentation. So our job now is to convince the members of the time allocation committees that we have to reobserve some of these variable objects. These will be very valuable data, very, very constraining for models, and very important in star formation in general. Thank you very much.
Okay, thank you for that nice summary of a lot of recent relevant literature and ongoing work. Questions? There's another mic around.
Everything is clear?
You can do it. Raise your hand.
Oh, thank you for the excellent review. I mean, maybe all the colleagues are overwhelmed. But anyway, so the minor comment. So regarding the interferometric observations, I mean, so infrared interferometry. So maybe, so for example, so you mentioned the disk size of FURI to be 0.3 AU, but it might be model dependent, and also, I mean, then the important thing is if the observed, so I mean, parameters agree with the conventional disk model or something. So maybe someone can dig that issue into, I mean, details in the future.
Absolutely. So that's actually planned for next step to tailor a model specifically for FURI that would reproduce the visibilities, the interferometric visibilities. Also, we have an ongoing project to make image reconstruction with the VLTI, not for FURI specifically, but for another object. That's work in progress. It's very costly because you have to use all 4 UTs for 8 hours and perhaps do it again. But that is one way to learn something in a model independent way. Of course, it's much more difficult to do this with only 4 telescopes than with ALMA, but we will try our best.
Hi, thank you for the really nice overview talk. Yeah, it was a lot of information to take in. But one striking thing to me was looking at kind of the 1,000 AU scales of the small dust. Looked really unique for each source, really big and extended and like kind of chaotic. But then once you go down to the millimeters, they're all seemingly compact and small and massive and smooth as far as we can tell. Is that correct, my interpretation, and is that weird at all? And is there something going on
I think there's an issue of sensitivity. So once you integrate hours and hours and hours and hours with ALMA, then you will start seeing the far away, the cold, the faint emission, and that basically was shown here. So it's much more difficult to trace such distant structures with ALMA simply because of sensitivity.
Hello, thank you very much for the nice talk. I am curious to know, maybe just a general comment, you can share your opinion on that. Do you have any comments on the trend of stellar mass versus the mass accretion rate? I mean, is there really any correlation that exists between the stellar mass, if I just straight plot on the x-axis the stellar mass versus the mass accretion rate? For the low mass case, for example, would I expect to have like a linear trend or a non-linear or any particular feat or anything like that?
I think there is a correlation. This has been done or plotted for many of the star-forming regions, for many of the mass ranges like Herbig stars and then to T-Tauri stars and then down to brown dwarf masses. Whether eruptive stars would fit into this trend, I'm not sure. I don't know if someone ever checked that. That's a nice idea.
Okay, thank you.
Well, at least some of the objects, this would be a question, yeah.
Right, I mean either from the mass accretion rate or maybe from the luminosity accretion.
Yeah, but it's time variable. So do you take the peak or the fading or the quiescent?
Where to locate?
There's an extra dimension there to take into account.
Okay, thanks for your comments.
Nice talk. I'm still puzzled by FU Orionis. And as you said, there is no jet, there is no outflow. But is there any evidence in the past or in the environment that there was an outflow? And I mean, where is it actually, the environment of FU Orionis? I'm not quite sure. Is it near a cluster or is it completely isolated star? Isolated binary star and the separation?
I'm not sure where inside Orion it's located, but there is a new result by Antonio Ales about an outflow. So it does have an outflow, a large, wide opening angle outflow. At least we know that there is also a large-scale scatter light nebula around it, so there must be more material in the immediate vicinity. There is a scatter light little arc, which actually was included in the criteria for a star to be classified as a FU originally. I don't know if this is still considered a required criterion.
Yeah, that's right. Originally, the single dish surveys, they missed the outflow. They classified, yeah, I think it was Neil Evans who couldn't find it. He found them among other FU stars, but not around FU itself. But with the ACA, we were able to see that. And the nice thing is, as Agnes mentioned, the blue shifted lobe, it traces well the reflection nebula. And a reflection nebula was one of the characteristics to qualify something as an a priori star or not. And I believe that Lee was going to say something. There is also strong wind seen, I think, in oxygen lines among this star. That is about 10% of the accretion rate. So what is the relation between this outflow and the wind? I think that's an open question that I would love if somebody has, love to hear an idea about that.
Okay, thank you.
Thank you.
And then, as a reminder, you should be thinking of your questions for all of our speakers.